Let me show you one more example on Thevenin's equivalent circuit, okay? We may have done that in the class, but let me just show you a different way to work on it. Oh, before we do that, something to clarify first. Oh, remember, I think we were looking at the circuit from the practice exam. It looks like this. A very weird circuit. Yeah, after seeing this example, I was also asking myself that same question, actually. All right, remember, so the question is, it doesn't matter. It could be a dependent source, could be something else, right? For example, we have a voltage source here. Okay. Is there any current flowing here or here? And why? Sometimes the easiest question will get you. Have to think about it. Why? I mean, it's so simple, but why? I was looking at this circuit by home. This is basically what I do every day. You have all different circuits, you put a common ground, short them to ground. That's what you do. Why? But we never think about that is if there's any current flowing through these wires, right? Are there any current flowing through that? That's just the one common ground, 0 volts. Remember last time I was telling you, I know there's no current, but I don't know how to explain that to you. Right? Why? Why there's no current? No. So in real world, you have all different circuits, anything, black box, right? Circuits to be built on the, can be a breadboard, can be a printed circuit board, whatever. You could have like millions of blocks for the integrated circuits, like the chips. You can integrate like 100 billion transistors on it. So you have just so many different components, and they all have a common ground, right? So they all have a common ground. And that's the same problem. So you have one block here, and you short them to the same ground to provide a 0 volts reference. It's gonna be a disaster. You have currents flowing into the ground lines over here. You are losing currents. It's just providing a voltage reference. We know there's no current, okay? But why? See? Such a simple question really gets you, right? I think it's the same for other sections as well. If you pick up a student from other sections, it's gonna be the same thing, right? Never thought about it. So what's the current here? I can assume it's I, okay? Right? It's the same circuit. So I know the current here is what? I know it's gonna be I, it's the same circuit. It's gonna be I here as well. Do you have anything to lose? It's all I, right? Anyway, such a simple problem. But keep in mind, you have all the different components, different circuits has a common ground. There shouldn't be any current flowing through that, okay? First problem. And another one I want to talk about, I'll give you one more example for Thevenin's equivalent, since there are 2 problems on the exam are asking to do RTH or VTH. Okay? Make sure you can do it. At least 2. I saw 2 this morning. Could be more. So this is a problem from the from homework 5. Okay, just example to go through this again one more time. 26, 40, 13.4, and this is 110 milliamps, 15, 4, 10 ohms. That's the entire circuit. The load is already removed from the output terminal, so there's no load. Don't treat this guy as a load. It's not a load. Usually the load will be connected to the two terminals. It's going to show you, right? It's going to show you RL, something like that. Okay, so this is not a load. Keep in mind. So load is already removed, and it's asking you the RTH, VTH, and possibly IN as well. If it's asking you to convert it to a Norton's equivalent circuit, and let's find out RTH first. Looking backwards to the circuit and short the voltage source and disconnect the current source. So we're getting this. It's disconnected, the current source is removed from the circuit. A and B, 10, 4, 26, 40, 15. Okay? So imagine that you have a little current being injected into the node over here. So it's being split into two branches, right? So 10 ohms directly goes back to B, so it's returning back to the whatever. So usually I don't want to assume too many variables. So basically, if you assume there's a V-test, right? If you have a V-test, so this current is going to provide an I-test over here, and that I-test eventually will go back to the cathode of the voltage source, right? That's a short circuit. So that's why this current comes in, split into two branches, and the branch current goes through the 10 ohm resistor will directly go back to the source. So that's why the whole thing here is in parallel with the 10 ohm resistor. Does that make sense? Okay, so this is one of the two branches. So this branch goes through the 26. You know you got a 26 ohms first, and then whenever the current flow arrives this point, what's happening? Goes through the wires shorted. So these two resistors are getting shorted. So directly goes back to the left side of the resistor, and then goes through the 4 ohm resistor and return back to the source. It's not going back through the 10 ohms because this is the shortcut. It's going to go through the cathode, right? It's getting shorted. That's why we know that the RTH is definitely 10 ohms, right? 10 ohms in parallel with something. 26 plus 4. 30, yeah. Oh, 26 plus 4. So 30 ohms in parallel with 10 ohms. That's RTH. What about VTH? VTH is the voltage at the output. So VTH is also VO. Sometimes you see VOC, open circuit. So that's exactly VTH, which is the voltage at this node. So for this example, how do we calculate VTH? Where to get started? We can use node voltage method, right? So let's just assume VTH. This is the voltage over here is VTH. So what's the current flowing here? VS, right? So this is VS. So it's 13.4 volts minus VTH. It's going to be over 26 ohms, so will be the current here. And you have the current, another current flowing into the node, which is 110 milliamps. Is there any current over here? No current. It's an open circuit. No current flowing into this wire. So no current. So all the merged currents goes through the 10 ohm resistor. And then what? Go back to B or go through here? It's a disconnect circuit. You have nothing here. Don't imagine anything. Nothing. Even no load. So the merged current goes through this one and then go back to where? The source. So it has to go through this guy to reach ground. So it's not going to the right. Since there's nothing, it shows you nothing, then it's going to be nothing. You have to trust it. This equals what? VTH over what? 14. 10 plus 10. 10 plus 4. How many variables, how many equations? One variable, one equation. You can get VTH solved very quickly. So you don't even need to assume a voltage here. You don't need it. Just for this case. What's that?
Wouldn't there be a different voltage after the 4 ohm resistor? Like there?
Mm-hmm. It's just the one current, so it's okay. There's no current flowing there. It's just one current.
Oh, so we're running parallel.
In series, they're in
Yeah,
series. So 10 and 4 are in series.
Okay.
And that's the voltage drop across the 14,
Yeah, that makes sense.
right? Directly goes back. Is it going here? Going up? It doesn't matter since we don't care. We only know this voltage is 0 volts. So we know the drop is going to be VTH. Is there any current flowing up? Going up? There's some current going down, so there's some current going up as well, right? Is there any current going up? Why? There should be some, right? Since there's the voltage here, that's 0. That's a resistor. There should be some current going over there, but we don't care. Do we care about that? So another question. Is this current the same as this current? That's right. No, they're not the same current since you have another current over here. According to KCL, they shouldn't. Unless this is 0 amps. Otherwise, you have 3 branches connect to this node. Confusing? Just use KCL, right? But we don't care about that anyway because we know VTH already. We know we are done. So lazy, right? No, we are done. For IN, so if you get VTH, what's the way to get IN? IN equals VTH over RTH. Keep that in mind. You can immediately get IN without transforming the circuit to something else. But however, sometimes it may ask you directly to find out IN, right, from the circuit. And I'm going to show you how to do it. So the way to find IN is you short the 2 terminals. Definitely you can always find a VTH first and then divide it by RTH to get IN, right? It's something we need to memorize, unfortunately. Okay? So RTH is RN since we use the same method to calculate to find the resistor for the Norton resistor or the Thevenin resistor. We use follow the same method, which is remove the low and looking backwards, short the voltage source and disconnect current source. That's what we did. Okay, how we do it, right? So If you know VTH, RTH, you can definitely find out IN. However, if you are not using the VTH, convert to Thevenins first, and just trying to get IN first, directly. So the way to do that is, you connect the two terminals with a wire. Okay, that's the traditional standard way to do it. Keep that in mind. Will never give you any issues and errors. Directly find IN. The way to do that is directly draw a wire across it, and use whatever node voltage method or mesh superposition, whatever you have to use to find out this current, and that will be IN. This is another thing you have to memorize. It's the method we have to cover. You have to know how to do it. So now let's see. If you have IN like this, is this one getting shorted or no? Yes, it's getting shorted. Okay, another thing. If I'm drawing a current source, 5 amps. If I draw a wire here, is this getting shorted? Is this getting shorted? Why? What does that mean, getting shorted? Physically. Yeah, voltage is the same. What else? The current is not going to flow through this guy if it's getting shorted. Right? That's by definition it's getting shorted because the current's taking a shortcut instead of going through the another component. What about this one? If you want to determine if this guy getting shorted, you want to see if this is having a zero current flow through it. Is it zero current? No. It's an IDU current source. We have to trust it. It tells you it's 5 amps. It's going to permanently run 5 amps through it. So you are not able to short it. So now you are pretty lucky you get a resistor. If you have a current source, making things complicated, you are saying, am I shorting the current source or not? You are not. Okay? But resistor is going to be shorted. So what's happening to the resistor? It's gone. Right? It's gone. So the circuit becomes it's gone, right? Only leave a wire here. So that will be IN. How do you find IN here? Let's use node voltage method, V1. You can get the current here. 13.4 minus V1 over 26 plus 110 milliamps equals same method, V1 over 4. Right? So you can find V1 first. IN equals V1 over 4. Done. Any questions on this? No? So make sure you can do RTH, VTH, Norton's as well. That'll be like 40, 60 points. Total 100 points is right at 60 points. KCL, another like 20 something points. Sign conventions, the polarity of the voltage and currents, another 20 points. Any questions? Any problem you want me to run? What's that?
Can you show some examples of how we write and apply a load resistor and why our 10 ohm isn't the load resistor here?
Usually they will tell you which one's a low resistor.
Okay.
If they don't tell you, it's not a low resistor. And usually they will connect it in the middle, right? Just I think they'll label as RL. They'll tell you. Mm-hmm.
Okay.
Yeah, good question though. All right, let's move on to the amplifiers. Is that okay? It's still Friday, right? It's still Friday. Just directly look at it, see what you need. Oh, one thing. Another thing you have to memorize. I hate to say that. So circuit 1 is not a place to learn internal structures of op-amps. So it's a triangle. Can do a lot of things. I can give you hundreds of examples of how this is being used in the industry. So this is the load. And usually it's RF, this is called R1, and that's V1. All right, so that's the structure. It's called inverting configuration. Yeah, a lot of new things, okay? You could either ground it or provide a negative voltage here. It could be very confusing, but now let's just try to seal this in your mind, okay? So this is a very typical connection of the amplifier, and this is called operational amplifier. So basically it's amplifying signals. It could be a very tiny signal from your heart, like the ECG, electrical cardiograph or something. ECG signal in the hospital, you see the patient has something connected to usually 3 electrodes, 2 here and 1 on the leg, and providing somewhere around like 10 millivolts voltage. So when there's a heartbeat, it discharges and has all the charges to your skin, and it's using a differential amplifier to collect it. It's usually in the level of millivolts, and that voltage is really tiny and noisy, so you have to use high quality amplifiers to amplify in order to see it. So you can see the monitor just next to the bed in the hospital, and shows the waveforms like this. So these are voltage signals. Is that amazing? And it's non-invasive. When you are doing your cardio ECG, sometimes it's called EKG, I think, in the US. I don't know the difference, but I have been learning this as an ECG. But sometimes you will hear EKG. It's giving you this heartbeat over here, and the signal, it's a surface electrode, and eventually will be digitized and acquired by the machine, and display it in the monitor and this is the voltage signal. It's a voltage signal. And it's not even being converted because your skin is directly giving that charge, and that charge is the voltage signal already. It's a differential voltage. From here, they're doing a subtraction, and the subtraction is this waveform. And it's being amplified and eventually digitized by the machine and displayed. Okay? And there are so many other different types of signals that can be collected from your body, like ECG and EEG. You know what is EEG? Your brain. Okay? You see the robots are being controlled by EEG. You put a little hand, and whenever you think about something in a certain area of brain, it will show a signal over there, and through some AI or filtering mechanism in the software, which is able to give a signal, send a signal to the robots, and help people to do something, right? Or moving something. For example, they are totally paralyzed, and they are able to use their EEG signal to type in the computer. Not that accurate. I don't believe it's like 100% accuracy right now. But when you are thinking something and that EEG, maybe just very simple terms, very simple English. The EEG signal being collected and then directly typed in the computer. And people already made that possible as well. So that's also a voltage signal whenever you are thinking and have some thoughts or events in your cortex, and there will be some charges appear on your head and being collected by the EEG machine and being amplified. That signal is even smaller than ECG. And there's another one called EMG, muscle, also being used for diagnostics. just have a very simple electrode put on the muscle area, certain area of the muscle, and it's able to collect electrical signal for diagnostic purposes. There are a lot of applications. And this is not just these are areas that you need a precision amplifiers because all the signals are tiny. So all the amplifiers we are going to use in this class are for relatively bigger signal amplification because they are not precision amplifiers. And you have to combine different types of op-amps into one bigger structure. If I have time, I'm going to introduce that, but I'm not seeing any assignments in homework 5 and tutorial 6. So I'm not sure if I have time to cover these precision amplifiers. But these are actually being used in the industry, and very important structure you need to know, right? And these ones are just for the textbook, like a toy, for circuit 1. So it's able to amplify signal, for example, from this node, all right? And here's the triangle shape. It has a pretty complicated circuit internally. You know, if you haven't done it, when I was an undergraduate, the teacher didn't even know how to build an op-amp. So they keep telling me like how to memorize all the certain things. I was pretty against about that strategy. So I didn't learn too much at all in undergraduate. But eventually I found out if I repeat the same concept for you guys again and again, just hopefully you can remember what's going on and what's required to memorize for this class. Okay, keep that in mind. Otherwise you'll be frustrated. So first, you have to remember the boring stuff. Get started, okay? First thing to memorize. You hate to memorize stuff, right? If there's a feedback, which means output, this is VL. VL is being shorted to the input, so these are inputs. All right, if there's a feedback, you have to remember that within the scope of this class, we're not dealing with all the little bias. Bias is a voltage difference, okay? So we just disregard that. So you have to know the voltage at these 2 points are equal. It's called virtual short. Oh, if there's a feedback, negative feedback. Okay, if there's a negative feedback. Why is a negative feedback? Because the feedback is connected to the inverting terminal, which is a minus sign in front of it. So if you have a minus sign in front of it, it's called inverting. So this is the inverting terminal. This is called non-inverting terminal. Okay? And this is the feedback resistor. That's why it's labeled as RF. It's not radio frequency. It's a feedback resistor. And this R1 is the input resistor. Usually it's called R1 or R-in. R-in sometimes. The second thing you have to know, no current flows into the 2 nodes. The 2 terminals, sorry. No current flows into the 2 terminals. So which means current arrives here. It's not going into here, not going into the triangle. It directly go up. Because it has a super high input resistance. For the input terminals, they have a super high input resistance. It's like a disconnect circuit. It's only holding the 2 voltages equal, but not allowing any current to get into the triangle. I was looking at the problem. You have to know these 2 at least. I'm gonna keep adding to it to the list. If I find out, you have to know more. But now just remember these 2, okay? In order to do any of the problems in tutorial 6. Now let me ask you these questions. Is there a feedback? Yes. Are they equal? Yeah? First on the list. Okay? Input resistance is infinity. It's gonna push all the current out. Or no, I shouldn't say that. It's gonna disconnect, similar to disconnect circuit. So eventually no current over here in this little wire. Is there a current here? Is there current flowing going to the ground? No, no current. No current going in, no current going out. So no current in this wire. Is there current here? Why? If the voltage here is ground, 0 volts, right? What's the voltage here? 0. They are equal. So what is the current? Flows through R1. I R1 is what? V1 minus 0 over R1. It's a voltage divider, right? No, it's Ohm's law. V1 is the voltage in. 0 volts. So the current will be V1 minus 0 over R1. And no current flowing into the triangle. So it's going to go up. And go through this guy. Is it going into the output? No, it's the output terminal. It's not going in as well. So it's going to go through there and go through the low and go back to ground. So let's derive the voltage gain since we care about the gain. You told me this is the amplifier, so how much is amplifying the input signal? So we need to know the gain. It's called the voltage gain. So here's V out. Here's 0 volts. Okay. V out minus 0 volts divided by RF, which is the current going backwards. And that current equals the current going this the negative version of the current going this way, right? Because it's the same, it's just one current, keep that in mind. Just one current. Going here, going up, going through the resistor, go back to output, right? Now we want to build a relationship between V out and V in. This is a V in. So V out minus 0, which is negative V in minus 0 over R1. It's the same current, just one current. Just the opposite way to do it. Well, I want to let you look at another example here using amplifier to build a different circuit. I'll show you really quick. See if I have it posted. Oh, this one. Oximeter is another biomedical engineering, biomedical parameter monitor. It uses a IR signal, infrared. For example, this is the finger. This is the finger. You have seen that clip, right? Put the finger and you can see a pulse as well. So it's not collecting voltage. You have to know that. It's not collecting voltage. Doesn't like the ECG signal collects the voltage and amplify it. So what this one does is, blood, your fingertip has blood vessels, right? So the blood is going to absorb oxygen. So it has oxygen inside your blood. And oxygen absorbs IR light. Have you heard about IR? Alright, so the spectrum visible. You can see all the colors from blue to red, and that's wavelengths. Okay, So this is usually like 470 nanometers as a wavelength of the light, and this is somewhere around like 750 nanometer. So all the light outside of the range will be invisible because this range is visible from blue to red. So this is called IR or infrared. This is called UV, right? So these are invisible. You cannot see it by our naked eye. So what's happening is the IR light it can be absorbed by oxygen and eventually reflected. So whenever your heart starts pumping blood into your fingertip, so there will be more oxygen. Oxygen goes up. If you have an IR emitter and a receiver, so that's a pair of IR. This is the IR LED. It's emitting, so it's sending an IR signal to the blood, your fingertip, and then if oxygen absorbs a certain amount of light, the IR light, so only leaves the unabsorbed IR being reflected back from your fingertip and to the receiver. So you're able to detect the frequency of your heartbeat as well. Why? Because your heart is pumping blood into your fingertip. So what's happening is you can detect the voltage at the receiver. So the receiver's voltage becomes this. Because you have blood being pumped by your heart to the fingertip regularly, right, or periodically. So the voltage change reflects the IR light being reflected by our fingertip or absorbed by the blood or oxygen in the fingertip and eventually received by the receiver. So if you try to measure the frequency over here, you can measure your heartbeat rate as well. That's how you do it. It's different from the ECG. ECG is just the voltage directly being collected. This is from light. So light absorbed by the blood, oxygen in your blood. Whenever it contracts, so the blood comes back to the heart, so you get less blood or less oxygen, and you are getting different signal received by the receiver. That's how that works. Okay, so this one, we had a 3-hour lab, and it was able to show this on the oscilloscope in the lab by building a circuit like this. You see all these are op-amps, right? So one of them is the precision amplifier, which is able to detect that little tiny signal. And eventually you need 3 stages, and it will be converted to a voltage and shows up on the oscilloscope. So you can use a cursor to measure it. Okay, this is something you can do for your senior seminar if you want. So the circuit is very simple. It's just the filters, amplifiers, and you can even use Arduinos to probe the voltage output. And Arduino has an ADC, which is the analog to digital converter. You can digitize it and display in a serial monitor like this. So you can design the oximeter just in a few hours, like 3 hours. And you can convert it to a PCB board as a product if you want. Okay? So what we care about is the voltage gain, right? Because the signals are tiny and we want to amplify it. So if you look at this structure, let's find out the voltage gain first. V out, RF, R1, V in, ground is a negative feedback, so 0 volts. Okay, Ohm's law, V in minus 0 over R1 equals, let's just directly use the left to right direction. So it's going to be 0 minus V out over RF. You want to remember this equation. It's just a simple Ohm's law. V in minus 0 over R1. It's giving you this current. It's not getting into the triangle, so it's going to go up and reach V out. So then you use 0 minus V out over RF. You're getting this. So simplify it. It's V in over R1 equals minus V out over RF. So V out over V in becomes negative RF over R1. Super important conclusion here. So this is called, if you connect the op-amp in this way, And this is called inverting configuration. Because the input signal is being put into being connected to the inverting terminal through a resistor. And that's the voltage gain of it. It's a negative voltage gain. But doesn't matter, like I told you guys in the very first class in the semester. So the voltage, if we want to determine the voltage is big or not, does the negative sign change the conclusion or no? No. It's a voltage drop, right? So negative 20,000 volts is still a big voltage. So what's happening is if you have an input voltage, a sine wave like this, and it's going to invert it to this and amplify it by this much gain. Okay? What's that?
So you have two in your on your website, so you flip it.
Yeah, have to. If you use this if you use this structure, you have to flip it twice. If you use a non-inverting, you don't have to flip it. Yeah, we'll keep working on this. We'll see you this evening for the exam, all right?